Okay, very happy to welcome Bogdan Batko from the Jagiellonian University, Batko. And he will give us a talk with the title Conley index methods in data-driven dynamics.
Thank you very much. First of all, thank you very much for the invitation, for the opportunity to be here to give a talk. It's an honor for me and real pleasure here. I would like to present an approach to the study of dynamical systems that are known only from data. Our methods will allow for global general conclusions about the dynamics on the basis of finite information. Traditional analytical approach to dynamical systems is possible, of course, only when a mathematical model is available. In many situations, in particular in biological, sociological, medical sciences, rarely the case. Instead, scientists by experiment can collect data, and then there is a question whether such a finite information is enough to get some global conclusions about the dynamics and how to do it. And in this context, new theories, new methods of interpreting data are needed, and in particular, topological methods attract interest. Topological invariants can be particularly useful because they are robust. The standard focus in dynamical systems is on understanding the structure of invariant sets. However, correctly identifying invariant sets may require correctly capturing the generator of the system to an extremely high level of precision, which is often impossible from a given finite data. Therefore, our methods focus on coarsely characterizing the dynamics rather than identifying the generator of the system. And our characterization is done via Conley index, an algebraic topological invariant, from which we can induce the existence and the structure of invariant sets, for instance, the existence of fixed points, periodic orbits, heteroclinic connections, or chaotic dynamics. My talk will be a kind of overview of a long-term project that originated about 10 years ago. So I will mention some of the results without the details, without proofs, just to give you some information about what we are doing in this direction. What we mean by the sample of a dynamical system? For us, it is a finite set, let's say A in the phase space, together with approximate images of those points under the generator of the dynamical system with discrete time, or together with a finite collection of vectors at each point of this set that represent the direction of sampled Q. And today I will focus on the first page. We have some results regarding the second point also. But today I will mainly focus on the first case when we have a collection of points and images under the generator of the system. In this case, in a pretty natural way, we can construct a multi-valued map from data. We discretize the space and being the data. At the end, we would like to have everything finite because we need to make computations. So discretization allows us to get the finite representation. So think one of the most basic representation of such discretization is via cubical multi-valued map. So imagine that we have some cubes. We have a cubical grid of the space and on the phase space, and we look at points given a box. We look at points that from our sample that fall into this point, and we have approximate images of those points. Okay, and we try to define value of this box under this map that we construct. So we would like to cover those images by elements of our grid. But at the end, we would like the homology computations to be possible. Therefore, we need the values to be acyclic. So this is not enough covering of those points. In one of there is probably not a unique way how to achieve that. In one of our papers, we use so-called sunflower enclosures. Namely, we find convex hull of points, and we cover by grid elements this convex hull. In such a way, we obtain such a set that we call sunflower enclosure. And in this case, this would be the value of our multi-valued map for this cube. And we continue with all the cubes in the domain. We also continue with edges and vertices. For instance, when we are interested in the value of the multi-valued map on the edge, we look at the cofaces of this edge and do the same with all the points that fall in all the cofaces of this. Okay, in such a way, we obtain a multi-valued map, which is upper semi-continuous and has basically and compact values. So our strategy relies on constructing a multi-valued map from data, then applying the Conley index theory for multi-valued maps to this multi-valued model, and identify isolated invariant sets, find topological invariance of those sets, such as the Conley index, and so on. So we make computations for this multi-valued model, and then the question is very important: how to relate the obtained results of the model with the underlying generator of the system. So a huge part of our work is devoted to this, and we have some results in this direction, which follow basically from the properties of the Conley index. I mean, from the homotopy, from the continuation property of the index. So here, I think the goal I talk maybe was a huge chunk. Yeah, it was interval analysis. Points, images, little interval. Yeah, images were also familiar. And this about errors. Yeah, you have to do the same, but three-dimensional. Yes, this is something which is in common in those two methods. But what Daniel probably does, because I more or less know his result, it's rigorous analysis via this interval arithmetic. When we know the model, then we can construct this map in such a way that we can rigorously guarantee what is the relation between the true generator and the model. Here, the situation is different because we don't know the model. We don't know the generator. We only have some points. So the representation, the multi-valued map is similar, but used in slightly different context. Okay. And what we can see here, one of our examples, I will go in more details to this example in a moment, how this graph of the multi-valued map looks like, and we have isolating the neighborhood in these index squares, and we can find transitions between those sets. Okay, now let me step back to simplest case. I mean to the one-dimensional case, because I would like to emphasize some important things about the construction of the Conley index. Namely, imagine that we have a dynamical system on a unit interval. As indicated, we bin the data. So assume that we use intervals of length 1/4 that define the bins, and using those points represent a graph of continuous, come from the graph of a continuous map, and we try to find both representation, the cubical representation of this data. So this gives us those two regions in blue. And what is the meaning of this region? This region in blue should provide a representation of a continuous map. So this representation, so in this form, it is possible because the domain is connected and the blue region is not. So it's not a good representation of a continuous map. Yeah. So one means of addressing this issue, what people usually do, is to expand this representation by adding some more regions, some more boxes, and in such a way that the representation contains a continuous map. So we say that the multi-valued map has a continuous selector. So we end up with such a representation, and which admits continuous selectors. And but this representation usually fails. What I mean, namely, this is a kind of minimal representation in our examples for all the functions that have fixed points at 1/2. Okay, so all the selectors of this representation have fixed point 1/2. But we cannot isolate this point 1/2 by grid elements via this representation, via this multi-valued map. Because when we compute for any grid elements intersection of this set and the image and the prep image, then we get the same. We don't have the inclusion in the interior of this set. So we cannot obtain isolation, we cannot isolate this point 1/2. Another way to say that we cannot isolate this point 1/2 is the fact that among the selectors, they're identical. Okay, so we don't. There's no chance to isolate this point 1/2.
But let me just add, because here it seems in some way artificial this half to half, right?
Yeah.
I mean, we could imagine that the real function doesn't go by here.
From 1/2. But
yes.
What are the choices? We could add, let's say, 2 boxes here and remove this one, or remove this one, add 2 boxes here. But the situation will be exactly in principle the same. I mean, we cannot isolate point which the selectors have. So this multi-valued representation is too crude. Okay. Okay. So that's the point, that the selectors will have some intrinsic dynamics which cannot be detected by this map, by the multi-valued map. Okay. But let's step back to our set consisting of to this representation consisting of two regions. Actually, we don't need selectors. For the homology computations, we need that the values of the map are acyclic. So we don't need selectors. So our remedy to this would be another representation, namely, let's define the value at 1/2 at this point at the whole interval from 0 to 1. So let's think about this representation. This is multi-valued map, which is upper semi-continuous with acyclic value, and try to use this map as a representation of our single-valued map. It does not have, of course, any continuous select. But now we can easily isolate this point by 1/2. Namely, when we consider this interval in the domain, then its invariant part is just this point, because the drainage is this point, and it's included, of course, in the interior of this. So this representation allows us to isolate this fixed point. And now, from the point of view of identifying the dynamics, computations that we make with the model should be considered as strictly formal, because in and of itself, it does not guarantee that there exists any continuous map which is capable to give us the dynamics that we obtain, the description of the dynamics that we obtain using the model. So we want to somehow prove that there is a class, and actually our claim is that indeed there is a class of continuous maps, large but explicit, of continuous maps that share the dynamic with the model. And this class of the map is the class of so-called approximations on the graph of the multi-valued map. So the definition is as follows. In the product space, we consider the max norm, okay? And by epsilon approximation, we mean a single valued continuous map whose graph lies in epsilon vicinity of the graph of the multi-valued map. So our claim is that the Conley index computation for the multi-valued group representation is shared by any single valued map which lies in this vicinity. And in some cases, in general case, we prove that such an epsilon positive exists. But for special functions, I mean for cubical functions, cubical multi-valued functions, we also can provide a lower estimate of lower bound for this epsilon. Okay, so that's the strategy. Okay, so we need in order to realize this procedure, we need the Conley index for multi-valued maps. So let me briefly present to you the definition of the Conley index. Okay, so we start with an upper semi-continuous multi-valued map with compact values. Here is and this multi-valued map is considered as the generator of the dynamical system. What is the solution? Namely, solution to given point x is a function sigma such that sigma, let's say at 0 is x, and we have such an inclusion, namely sigma at time n+1 belongs to f of sigma of n. So here is the difference. In the classical case, we have equality here, yeah? But now we have multi-valued map, so we have inclusion. But this also means when the values of the multi-valued map are not singletons, are larger, that we have multiple forward solutions. Okay, so that's the key difference between single-valued dynamical system with discrete time and the multi-valued one. That we don't have uniqueness of forward solutions. Okay. That's the key point. And the definition of invariant part of set N, namely invariant part of N, is the set of points through which there exists a solution which is contained in N. So we impose here only the existence of a solution. So they may be, to a given point, they may be many solutions, many solutions, right? The point belongs to the invariant part of the set if if it exists at least one solution in which state inside the set. So some of them may leave the set. If it exists at least one which stays, then we say, okay, this point is in the invariant. So that's the definition. And the definition of isolation. Formally, the definition is exactly the same as in single value case. Namely, we require that the invariant part of the set is contained in the interior of N. Okay, so let's say the same as in the, but the consequences, of course, because of the non-uniqueness of solution. And interior. In the interior. The construction also in the single valued case of the Conley index requires such an isolation. Yeah. Invariant part should be in the interior of. Okay. So
yeah, I think one would imagine there is an attractor and
okay, and a set. Set is invariant if it's equal to its invariant part, so classical definition. And the set is called isolated invariant if it admits an isolating neighborhood. So its neighborhood such that the set is its invariant part. Okay. And now, the main tool in the construction of the Conley index is the so-called index pair. That is the pair of two sets, P2 subset P1, of two compact sets, P2 subset P1, subset N. Index pair somehow organizes the dynamics in the isolating neighborhood. In this, in what sense? Here is the adaptation of the classical definition to the case of multi-valued maps. Both sets, P1 and P2, are positive invariant relative to N. Okay. This condition gives us a kind of isolation. Invariant part of a set is in the interior of P1 and P2.
But we're in N common.
If N with respect to N. This
it's the same notation you just it's the same notation as before.
Yeah.
You just added explicitly the F.
F, yeah. Added explicitly F. Invariant, yeah. Invariant of N with respect to F is a subset of P1 minus P2. So okay, we can draw such a let's say in such a way. Okay, so this is P1, this big set. Here is P2 and P2, and assume that we have, let's say, fixed point, saddle point. Okay, so this would be an index pair. Both sets P1 and P2 are positive invariant with respect to the isolated neighborhood, and invariant part should be in the interior of P1 minus P2. This is the second point. And the classical definition of the index pair requires that f of this set, f of P1 minus P2, is a subset of. So this is the classical definition of index pair.
Why did you write P2 contained in P1 when you were here? And for P1 and
P1 is this set, and P2 is a part of this set, this exit set. When we look together at axioms A and C, then we see why this set P2 is called exit set. Maybe this condition says that when we are in P1 but not in P2, then we cannot leave N in one step. We should stay in N. So the only way is to enter P2 and from P2 escape the isolating neighbor. So the meaning of this set P2 is exit set. Okay. So we can stay here as long as we wish. We can stay in P2 also as long as we wish. But once we are in P2, we cannot go back. We can stay here or leave. Plus, we cannot escape the isolating neighborhood in one step just from here. First, we should enter P2 and then leave. So that's how the classical index pair works. Okay, and when we look at our toy example, then we immediately see that there is no chance to have such index pair in the multi-valued case. Namely, let's have a look that the image of 1/2 is not contained in N at all. So we cannot have this. In this case, we don't have this.
Probably, yeah, but could you indicate what are P1 and P2 in the first one?
N is this interval involved. Okay, so P1 and P2 are subsets of this set. So P1 minus P2 is a subset of this line. 1/2 should be in the interior of P1 minus P2. Okay, and the image of 1/2 is not contained in this interval. So P1 minus P2.
No, but I meant to know, I thought I'm asking a trivial question. I just meant how do you see A and B? If you now show that C doesn't hold, but to show that A and B hold with respect to which
the P1. In this case, the index pair would be P1, the whole isolated neighborhood,
okay,
and P2 consisting of those points, left point and the right. So P1 and P2 are satisfied.
A and B.
A and B, but not. So in the conclusion, in the multi-valued case, there is no chance to guarantee the existence of index pairs. So the main, so index pairs are no longer useful for the construction of the concept. So we need to change the construction. And what we do? We introduce new notion of so-called weak index pair, where we remove this point C and replace this point just, but the following conclusion, namely that P1 minus P2 is a subset of interior of M. Okay? So weak index pair has the same first two conditions, properties as standard index pair, and this is much weaker. And in this simple example that we had P1, it was, let's say, kind of interval AB. So P1 is the whole interval, and P2 just endpoint. Okay, so of course this is weak index pair in this. And what about the exit set? Now we can immediately leave P1 minus P2. We don't need to enter this definition, allows to leave isolating neighborhoods just in one set. So from this we can go out without entering P2 because we remove this condition. So okay. But what we have is a kind of property which can be viewed as something similar, much weaker but similar. I mean the F boundary of P1 included in P2. What does it mean? What is this F boundary? We consider the image of P1 minus P1 and closure of this set and intersect with closure P1. So it is F boundary is a part of boundary of P1 determined by the image of F of P1. Okay. So and the condition that follows from this is that this F boundary is a subset of P2. Is a subset of P2. So we can leave. Okay, so this is the somehow related to this notion of exit set.
How? I mean, how do you interpret this boundary? And geometrically.
Okay, so if we have, let me draw. Okay, let it be N. And F of N, okay, and pre-image of N. This is what we usually do in an isolating block N. So the invariant part of this is included somewhere here. So we can define in this case an index pair in the following way, namely, we take as P1 this set together with some neighborhood of this set, right, which is included in the interior of N plus this guy. So this would be P1. Okay. And P2, what should be P2? And what about this one? The image by F, by this set, on the boundary of P1 should be contained in P2. So in this case, P2 should be something like that. P2 should have this orange set as a subset. So in this sense, okay, in this sense, P2 P2 should contain at least those two pieces of the boundary of P1. Okay, so my intuition is that we can, escape from here, but not in any direction, but only through, let's say, over, not through, but a kind of over, we jump over this barrier and this barrier. So that are places, directions when we escape from isolated neighborhood. So this is just my intuition. Okay, formally this inclusion holds. Okay, but in order to leave the isolated neighborhood, you don't need to go through. You don't need to enter this. Okay, and a huge part of our work is to guarantee that actually any isolating neighborhood admits a weak index value. Okay. And the precise statement is that we can start with an arbitrary neighborhood of invariant part of M. So we can take any neighborhood, and we can find weak index such that P1 minus P2 is included in that. Okay, so here is this neighborhood W of invariant part, and we can find such an index that P1 minus P2 is included in this set. So we can find index that arbitrarily closely isolate the invariant set. Okay, so and what we do next. So we have weak index pairs, and from the positive invariance of sets P1 and P2 with respect to N, it's easy to see that the restriction of the multi-valued map to P is a map of pairs from P to this pair. P1 plus everything outside invariant interior of them, and P2 plus, right? So this first set is P1 plus everything outside the neighborhood, and the same for P2. P2 plus everything outside. By positive invariant, this restriction is a map of those pairs, between those pairs. And now the inclusion from P into this pair induces isomorphism in the Alexander-Finite cohomology. This is easy to see as the strongest decision property of the cohomology theory. This is because when we compute the difference between P1 and minus P2 and this set and this one, they are equal. Okay, so we acquired that the map on the difference is bijection, but of course the inclusion is, so it induces isomorphism in cohomology. And this allows us to define so-called index map associated with weak index pair. Namely, we take let me draw. We have P, we have this pair Tn of P and P here. Here we have F restricted to P. Here we have inclusion, okay, which induces isomorphism. So on the level of cohomologies, map induced by F would be here, and map induced by inclusion here, and we can invert this map because it's isomorphism, okay? So the composition, so this is the index map, the composition of the inverse of the map induced by inclusion with map induced by F. Okay, so index map is an isomorphism of this model. Okay, and on the top of that, we apply so-called Lerre factor to the pair, to this pair. We apply Lerre factor. Lerre factor. What does Lerre factor? It's a factor from the category of endomorphisms to the category of automorphisms, of isomorphisms. So the construction, I don't want to go into the details, but what is the construction? It is a two-step construction, namely.
What is later there? N star? N of what?
H.
H.
H star of P and index map. So we have this pair module and endomorphism of this module.
Yeah.
And to this pair, we apply the Lerre factor, which gives us which produces isomorphism from this endomorphism. Namely, the first step is that we divide this endomorphism by so-called generalized kernel. Generalized kernel of map P is the union of kernels of iterates of n, okay, of n, okay, and we consider the quotient space. We divide the space by this generalized kernel. In such a way, we obtain what we obtain, and consider the map induced in this quotient space by this map on the level of okay. We go to let's start of P over G care of IP, okay, and we consider map we induced in this quotient space by IP in the standard way. Then this is monomorph, okay, and the next step when we get a monomorphism, we just restrict the domain and codomain to generalized image. Okay? In such a way, we obtain an isomer. Okay, so that's the construction. That's the construction. So the key point is the index map, and then the reduction of this pair, and we use this reduction of this pair as the definition of the Conley index. So the Conley index is the graded module, the reduction of the module of P in cohomologies and index map for weak index.
And can you remember Alexander cohomologies change the finite set of points?
So here, what is we need for the construction strong excision problem. So it could be exchanged by other cohomology theories, but we need strong excision. So, but for nice sets, it doesn't matter. And what is important? The important thing is that what we define is invariant of isolated invariance, namely that the Conley index does not depend on the choice of isolating neighborhood and does not depend on the choice of weak index first. So this construction guarantees that we really have an invariant. And proof is pretty long and technical, and it involves several properties of weak index persons and so on. So I don't want to go to the details of how it works, but hopefully, but we have the construction of the and now the properties of the index. Again, I will not go to all the properties of the index. Let me just mention the homotopy property, because from the point of view of application to some dynamics, it is important. So assume that now X is locally compact metadata space, lambda a compact interval in R, okay? And we consider upper semi-continuous map from this product lambda cross X into X with compact values, which is used to as the generator of the dynamical system. We use the following notation, namely we denote F sub lambda map, which at points X is equal to F of lambda X, and F lambda is the generator of the dynamical system. And we refer to this family of maps as parameterized family of discrete multi-valued dynamical systems. And what we can prove, mainly, if we have an isolated neighborhood for some F lambda 0 from the interval lambda, okay, then N is also isolating neighborhood for F lambda of lambda sufficiently close to lambda 0. So one may say that the Conley index does not depend on small perturbation. Okay, does not depend on small perturbation. And we also can prove the following property, continuation property, namely, if N is isolating neighborhood for each lambda from some range of parameters, then the Conley index does not depend on that. So here we have existence of such an interval, and here we have the property that as long as isolating neighborhood does not change when we change the parameter, the Conley index also is the same. Okay, so this is crucial in our.
It is important here that the parameter is one-dimensional, that you take it from an interval and not some.
I don't know. Yeah, I don't know. It is in the how it is proved. It is important that it's intervally, but it's it's interesting.
Mm-hmm.
What about other parameterizations? Okay, I don't know.
Mm-hmm.
Okay, and now theorem which actually relates the homotopy property with approximation that I mentioned briefly at the beginning. Namely, the result is as follows: when we assume that X is right, in compact absolute neighborhood exact, and F is upper semi-continuous map with convex and compact values, N is isolating neighborhood, then there exists positive constant epsilon, such that the set of epsilon approximation is normative. So first we prove that there exists continuous maps that approximate the multi-valued one, and the second that the Conley index of the multi-valued map is the same as the Conley index of any such epsilon approximation. So here existence of such epsilon. Okay. In this case, we can prove that such an epsilon exists. Epsilon approximation exists, and they share the Conley index with the multi-valued one. And we have shown this result, but when we assume that we have cubical maps. When a map is cubical, I mean, map is cubical if the domain is cubical, values are cubical of the multi-valued map, unions of cubes, okay, and that the map is constant on cells associated with cubes. So in the planar case, the value at each point of the square without the boundary should be constant. Okay, so it's constant on cells. So in this, when we assume that n, the isolating neighborhood, is a cubical set also, then the conclusion of this theorem holds for any epsilon less than or equal to 1/2 delta, when delta is the size of the cube. So in case of cubical maps, we have lower bound for this percent. We know that it exists, and when it's less than half of the grid, okay, then so any continuous map which lies in the vicinity up to one half of the length of the rectangle in the vicinity of the multi-valued map shared with the multi-valued one, the Conley index. Okay. Now, how we can make use of the Conley index in order to detect some implicit dynamics? What about orbits? Assume that we have a locally compact metric space, and now F is a discrete dynamical system, singularly one. And what we assume that we have an isolating neighborhood, which is the union of pairwise disjoint compact subsets. Okay, and assume that we are interested in the following question. What about the invariant part of this blue set? And more specifically, for instance, is there an orbit which those sets in such an orbit? Okay, so how we can use the Conley index to prove that such an orbit exists? Okay. It's not enough to just compute the Conley index, because then using, for instance, the existence, the Rogowski property of the Conley index, we would get that there is, for instance, that the invariant part is non-negative, but does not necessarily mean that we have such an orbit. We don't know what is the structure of the invariant part. Okay, so what we do? We construct so-called extended space, namely we consider copies of our space formally.
But in that example, would it be possible to take the union of these three? It will be also isolating.
The union of those three, yeah.
So isn't it a question about the minimal isolating? Because we started with the form. Now I can ask what is the minimal one?
Each piece of this is the isolating neighbor. Okay. But the invariant part may be empty then.
Why?
The union also.
Contain periodic character of periodicity.
If you would like to have the periodic character, yes, then you
Also Conley. And there exists something.
we
I get point of view of others field.
yeah. I'm not sure if I am addressing correctly your question.
I'm not sure whether I answered this. Okay, you know,
Isolating was that it was equal to invariant, yes? And it was in.
No, invariant part of the set is a subset of the interior, and that's it. So when you choose any of those guys, any single one, then it's still an isolated neighborhood, but it may happen that the isolating part of the set is empty. Okay? So it may isolate empty set. Okay?
There is something that we did not figure out in the sense of homomorphism.
Yeah. It's
The matter of the space is not connected. See, look from what topic is more about I'm not sure what I mean. Okay, but if we have nothing to the variant, then we have kind of this method to expand the fraction of the
yeah, but
and that it's three disks of the same composition.
yes, but what we would like to have, we would like.
problem is I don't really sure whether I understand the definition.
Okay, but we would like to have a tool to guarantee that. Okay, let's check if there is if there is a periodical cycle. Yeah. So why is
Which is I'm sure whether I follow the definition. No.
okay. So what is this extended space? We consider DP topological group with addition modulo P and the discrete topology, and this extended space is the product of those two spaces. Okay, and on this extended space we define dynamical system by this problem. Namely, the pair xi is mapped into f of x, so the fact variable exactly as f does, and the second we change the level, okay, in this construction. So we now, if sigma is a sequence that we are interested in, okay, that the presentation is a sequence that we are interested in, then we can consider on appropriate levels copies of this. For instance, N3, then N4, then N4 we put on the next level, and N2 on the next one, and so on. Okay, so this set, it turns out that this set, namely when we take isolating neighborhoods species, isolating neighborhoods here, on proper levels and take the union, then it is isolating neighborhood for this extended C. This needs proof, but it's true. Okay, and we are interested in invariant part of this set with respect to this extended C. Okay, so why we are interested in constructing this extended space? Namely, now when we prove, assume that we can prove that S sigma is non-empty. then by the definition of the extended system, it must be orbit that goes from this to this to this and this. Okay?
What is the importance of the parameter P here? P is the one, how many levels?
P is the length of our orbit. Okay, so now we are interested in an orbit going through presets. So we consider here P equal to 3. Okay, so it depends on how many sets you choose. And you asked about the invariant.
Maybe let's just a formal trick. How this trick obtain something and you want to eliminate the possibility that something sits only in one component.
Yeah.
So if it sits in one component, when the component goes next component. What you did is even better, but it was sufficient to continue with not the period intersection.
Yeah,
Of union in each of the components.
I'm not sure if I understand, because when we just asked about the invariant part of this,
Okay, there must be something.
I think that there is something,
Okay.
but it may be, let's say, fixed point here.
Fix it point because it jumps to.
I don't know if it jumps.
But you made it check.
I would like to prove that it jumps. I don't know.
Well, so okay.
Okay.
Maybe understand that it would be interesting to see how in a completed pattern you can indeed prove
Yeah.
after you multiply.
Yeah.
You just forget all the
The arrows mean that we are interested only in the question if there exists a trajectory which goes along. So we don't know.
we can over.
Yeah. Okay. And how we proceed? How we use the Conley? Mainly when we take a weak index pair in this space, then we have index map associated with this index pair, which is called IFP. Okay, and we can define the homomorphism from the product of those modules into itself in the following way. Maybe we it's probably better to look at the matrix representation than go through the formula. But here is inclusion, here is projection on some component of those products. Okay, so here we have our sequence which we are interested in, and we put from our from the index map, from the matrix of the index map, okay, some entries which are related to components defined by sigma, let's say sigma 0, okay, sigma 0 to sigma pi minus 1, and so on, and so on. Okay, from sigma 0 to sigma pi minus 1, from sigma 1 to sigma 0, and so on, and construct a block map. Okay, so it's kind of artificial map constructed just by taking some pieces, some blocks of the matrix of the.
Can you repeat what?
Sigma 0, that are the indices of our sets. So in our case, sigma 0 would be 3. Sigma 1 would be 4. Okay, so this is our sequence. 3, 4, 2. Right? So we take from generators of the part of weak index sphere associated with this guy, some part, and put it here, and so on and so on.
And what is known and what is unknown in this stage?
Index map, we can compute, we have isolating neighborhood. So we have index map for the isolating neighborhood. When we compute isolating index map.
You mean for when we take the four, the union of all of them?
Yeah, the union of all of them, then we have the Conley. So what does it mean? That we have an index map. So think about it as matrix representation. And now we take some pieces of this map according to the transition and construct an endomorphism. This is pretty artificial, but it's nice because what we can prove, namely that in this extended space, we can find a weak index sphere such that sigma I, this artificial map, its iterate, its fifth iterate, is conjugate with fifth iterate of the index map associated with this extended group. So this is a theoretical result. The key point is that we have this conjugation. What does it mean? It means that we don't need to find this map in the extended space. It's enough to take some information from the original index map. Okay, so that's the reason why you are interested in this guy. It has this nice property that finding, constructing very easily this guy, actually what we construct corresponds to the index map in the extended. And in practice, we don't want to construct all the time the extended space. The key point is that we can extract information about what's going on in this extended system from the original. So this is this is it. Okay. And so how we can do this? Namely, the assumptions are the same as before, and we can prove that if this endomorphism IP is artificial one is not important, then there exists trajectory in the union, in this original system, in the union of those sets, which goes to the pieces in the prescribed order, in the order defined by this sigma 0, sigma 1, sigma 2, and so on, by this sequence. Okay? So, how it works? Namely, we apply the Warzewski property to this extended system. Yeah. If I sigma is not important, then it means by the conjugacy that the index map in this system also is not new, meaning the Conley index is non-trivial. If the Conley index here is non-trivial, it means that there is non-empty invariant part of this. And this non-empty invariant part must be this trajectory visiting the prescribed order. So this is how it works. Okay. So the extended system is constructed only for proving. For proving here, yeah? And we can also, instead of this I sigma, we can use easier representation, namely from index map, actually from the index map in the original space. We can choose some columns which are associated, which are defined by this by our sequence sigma 1, sigma 2, and so on, and consider compositions of those guys. G sigma pi minus 1, and so on and so on, G sigma 0. Okay, this is the order in which we are interested in. And we can prove that this composition is again conjugate with our artificial map I sigma and conjugate with the index map in the extended space. So we can also use we can prove the following. I mean, if this composition is not known, then it's guaranteed. Okay, so we can use it. In practice, this is easy to apply because we have the same size of the matrix. It does not depend on the length of the sequence we are interested in. For proving it was easier for me to go through this step with I sigma, but all those things are conjugate. Okay, and now we can also have a stronger conclusion when we assume that the Lefschetz number of the iterates of this guy I sigma of all the composition of this moment, the Lefschetz. So we can apply the Lefschetz type fixed point theorem to our map. I am afraid that I don't have time to go to the sketch of the proof, but so when we assume that the Lefschetz number, not only not impotence, but the Lefschetz number is non-trivial, it guarantees periodicity of this orbit. Very so what we could expect, I think, from the Lefschetz number. So this is
guy like Lefschetz forward.
yeah. And one of the most powerful thing about how we can use the Conley index to describe the dynamics is that we can, from the Conley index, we can construct semi-conjugacy with two known dynamics. For instance, to symbolic dynamics. So this is pretty standard notion of transition matrix associated with linear map. So I think I don't need to go to the details. And we say that linear map, that the homomorphism is Lefschetz complete if such a composition has non-trivial Lefschetz number for any sequence which is admissible by design. So Lefschetz completeness means that all those guys, for all such sequences, Lefschetz numbers are non-trivial. And here we have a result that involves this Lefschetz completeness. What does it give us? Namely, assume that, as before, that the isolating neighborhood is the union of these joint parts. And we have an index map. And we assume that this index map, associated with weak index first in N, is Lefschetz complete with respect to this decomposition. Okay. Then we prove that there exists a semi-conjugation between F on invariant part of this set and the fixed dynamics on on a finite number of symbols with symbolic dynamics where A is transition matrix, so here are frequently admissible by
These give you the upper bound of the F, right?
Yeah.
But can you also say something about the jump? The gap? Like we have a map from the symbolic shift to our system.
Mhm.
Can you say
The opposite way. I don't know. This is only the lower. Yeah. I don't know. Yeah, we only
Lower
can
bound.
construct semi-conjugacy. So we have the lower bound from the complexity of the
wait, now? Wait, what is the direction of the map?
data.
This is the continuum conjugacy, right? So we have some, let's say.
Semi-conjugacy.
Okay, but what is the direction of the map?
From our, let me draw. From our, we have invariant part. Yeah. Here we have shift dynamics. Here we have our map F, and semi-conjugacy goes this direction.
Like that.
Which means that our dynamics is at least as complicated as this one. So this is lower bound for the complexity of and okay, some example how it works, how we can apply. So we have some results. We started with Henon map. We sampled the Henon map and tried to describe the dynamics just on the basis of data that come from the iteration of the Henon map. So this formula which is actually known is used by us just to produce sample, and the rest is exclusively based on a sample. So we consider
The standard panel, except that instead of one variable is xy.
yeah. So it's kind of we have yeah, we have experiments in 2D, we have experiments in 3D.
That's one dimension.
Okay. With values like aura. And okay, so we consider the set of peoples, xi constituted three numbers coming from this Henon map, and we consider shift map. This is shift by defined on this. Okay, and we choose a being of R3 based on some size of this. This is the experimental setup, and for this map we construct a multi-valued map, which is a sunflower enclosure of this. So we start with points, with images via this map, and for points and the images via this map, we construct a multi-valued map as a sunflower enclosure. Okay, what we have. Mainly, this is the graph of the map. And using our algorithms, we were able to find isolating neighborhoods, which consist of 5 disjoint sets, N1, N2, N3, N4, and N5. There was the disjoint. Okay, so this is isolating neighborhood for the sunflower enclosure. We can find weak index first. P1 and P2 are in red and black here. Okay, so this is part of the P2, part of P2, okay. And we get transition, gravel transitions for this multi-valued map. And what we can prove, what we follow from the theory here. Mainly, when we consider a time which is delta half, then we know that the set of a chain approximations is non-empty. Okay. Next, this compact set that we found for multi-valued map is an isolating neighborhood also for any such epsilon approximation. Okay. And we can prove that there exists a semi-conjugacy of F on subset of invariant R onto the subset of finite type on 5 symbols with this transition matrix. So we have a semi-conjugacy such that for every periodic point in this space, or any periodic point in this space, there is a periodic point in the original space, which is apprehended by the conjugacy. Okay, and in particular, F has positive topological entropy on the invariant part of this. So this is how our result can be applied, for instance, to the example. We have similar result for Henon 2D. Okay, here is the isolating neighborhood that we were able to find for 20,000 points. Okay, this isolating neighborhood consists now of 6 pairwise disjoint sets, and the conclusion is similar. And we can also prove, here is an experiment for 2 periodic orbit. We can also prove the two periodic orbit for planar case and Henon map.
Is it possible to use this approach to make some rigorous conclusions for the original Henon map? Because this is, as I understand, it's slightly different.
It's slightly different.
It's not the same map that you consider.
Yeah, so we will go for any approximation within, and then it's also to for the original.
Not to the origin, because this would require from us to know that the original Henon map is one of these approximations, which we don't know.
Because I just read that the Henon factor is connected. It's not. So what is the meaning? So this is the result about the entropy of any epsilon approximation of a certain set value map.
Yeah.
This.
So and now the question, of course, is open if the true generator of the sample is among the approximations. So this is this is not guaranteed. But what we guarantee at least is that there is large class of single valued maps which produce the dynamics that we detect via the multi-value.
I think the better question in this case, which is how the entropy bound that you get, can it be, is there a way to prove that it holds for the original?
For the true.
Because then, then it wouldn't, there will be no contradiction. Because on one hand, you will not have a map to a symbolic space. But maybe by another technique, you will be able to inherit the entropy result.
Yeah. But it's hard to, as long as we don't assume anything about the sample, about the map from which we sample, about the properties of the map. If you have just data, then it's hard to. I think that I don't know if it's
No, that's
possible to. Yeah.
No, but the question is, with the limit of epsilon goes to 0, you could show that there exists a positive epsilon 0, such that if epsilon is less than epsilon 0, then you can say something about the entropy of the Truman.
Of the true map, by the true map, you mean in this case the Heron map?
Yes. Because I think there are other techniques that allow you, I think, by model that give you regular results on the entropy of the Heron map. No?
Yeah, but it requires, as far as I know, the knowledge about the analytical model. Yeah? Because you, yeah.
So you don't
I don't
more or less somehow
smaller and smaller beams. This is how it works on the level of experiment. So we see that really that when we go to smaller and smaller beams, our tools are getting better and better. But this is what we see by experiment. And now the question is how to prove that really, asymptotically at least, yeah.
So this is open.
This is open, yeah. The problem is when the grid is too coarse that we cannot detect much via the multivariate. Then we subdivide and and we see that our tools behave better and better. But in practice, of course, there is also some limit of this procedure. Namely, when we assume that we have just finite collection of data, then we cannot go to finer and finer meshes because at some point we have some boxes in our discretization with no sample point. So we cannot continue the construction. So this is obstacle. And this is why actually we started also to study the application of some statistical methods in this direction, Gaussian processes. Namely, we have some results which go in the following direction. Namely, we start with a sample, which may be small, and we try to fit to the sample a Gaussian process. We use machine learning algorithms to estimate parameters, and we have a model, Gaussian process model. And now, to construct the multi-valued map, we query the Gaussian process about, when we have a box and we already tested how to construct the multi-valued map, we ask the Gaussian process, okay, what do you predict? And the Gaussian process gives us the distribution at the output. So what I have, it's not just one point, but the distribution of the variable at that point. So I can use confidence interval for this value. And then I try to cover this confidence interval, but the value of the multi-valued map, just to guarantee the confidence of what you are doing. It works like that. We start with given confidence, let's say 95%, then use appropriately large confidence intervals from the output of the posterior Gaussian process, construct the multi-valued map, use it to make Conley index computations, and we get the dynamics. And then the results are up to some confidence. And then, of course, still there is a question, what about the relationship between the true map and the Gaussian process?
Maybe one could try to think about a situation where we work with the multi-valued function, but we have also some knowledge about the invariant measure of the true map. So this is the additional. And then, for example, if it's true that when epsilon goes to 0, all the approximate solution, their invariant measures weakly converge to the truth. Would this be enough in order to guarantee that the entropy bound is conserved? So like what?
I see your point.
Okay, I think it's time for us to thank the speaker.
Thank you.
Are there any questions?
Here, the diagram, this set, and variance and can't offset the book that we made with Conley. On the picture, you have trigger situation, one settle. And then, of course, sigma is 1.8.
But the applications are when you get a lower bound, a positive lower bound for the entropy. So if it starts becoming interesting.
So having, so your error will continue, we need to get some counter.
Exactly. But it's apparently the Hammond case, the attractor instrument. So you see the limit of the system.
So maybe the statement is that there is a subset of the invariant set, which is
Yes. Subset of this.
Yeah.
I mentioned that. Yeah.
You look for
The semi-controversy may be not just between the whole invariant, but some.
It's not yet.
So this is what was written on my slide.
I learned it from the scaffold tool. That people try to prove existence of something by chains forces. Anyhow, there are some forces in the way by constructing various.
So definitely, okay, I was not precise. Definitely, the semi-conjugacy is from the subset. From the subset onto the subset.
Maybe three.
It may be true.
But is the statement that, okay, on S, the map from S to sigma A is onto? Onto, okay. So at least it gives a...
Yeah, and continuous and onto this.
Trivial rotation with zero.
But then probably the same would be applied. Then probably the second can be applied. Because there is this lecture
Yeah. It's the function.
Okay, let's thank Bogdan again.
Thank you.